Hello, I'm Vincent Lauinger and I'm from the Karlsruhe Institute of Technology. I'm very pleased to welcome you to this talk about blind equalization for coherent optical communications based on variational inference. I work together with Fred Buchali from the Nokia Bell Labs, as well as Laurent Schmalen from the KIT. The motivation for this talk is the great demand for blind equalizers, where the safe data rate can increase the FEC overhead or data throughput. These algorithms have to be flexible and adaptive, and they must support higher order modulation formats and probabilistic constellation shaping. So far, the state-of-the-art algorithm is the constant modulus algorithm, the CMA, and its modification, the multimodulus algorithm, the MMA. However, the CMA is ill-matched for higher order modulation formats and probabilistic shaping, and the MMA suffers its high implementation complexity and its low convergence rate. So ideally what we want to have is a maximum likelihood-based equalizer. This, for instance, has been considered in GW92. So maybe let's have a look at our problem and describe it and see what we can do. So if we consider really some transmission channel theta with some input x and some output y, what we want to have is the maximum likelihood estimation of the channel. However, the likelihood of the channel we usually don't know. So what we know is the P of x, so the a priori distribution of the symbols, and usually we can model quite well the whole transmission system's likelihood. For instance, by a frequency selective AWGN channel with some channel impulse response H and some noise variance sigma W square. If we now want to compute out of this the likelihood of the channel, we would need to sum over all possible input sequences x. And this, of course, gets intractable. So we need another solution. An idea is variational inference via a variational autoencoder to solve this problem. For this, actually we need to introduce some decoder function Q, which is a parametric function with y as input, so the received symbols or the received data, and which outputs an approximation of the a posteriori distribution. So this has been applied by CP18 to some simple toy model, which actually is not practical for use. So let's really go a few steps back and derive this in a really general form. For this, we start again with the ML criterion, and the log likelihood we can rewrite as with this expression. So we have two terms. The term on the right hand side is the Kullback-Leibler divergence between the variational approximation and the true a posteriori distribution. The Kullback-Leibler divergence is a measure for similarity, and it's always non-negative. Hence, we can define the term on the left-hand side as the evidence lower bound, meaning that if we maximize now this elbow, eventually the Kullback-Leibler divergence becomes zero, meaning that we can really approximate maximum likelihood. So now we can use this elbow as loss function, and we can again rewrite this into with two terms, where A tries to shape the Q's similar to P of x, so to the a priori distribution of the the input symbols. So here we can really easily incorporate probabilistic constellation shaping. And the term B matches the equalizer output to the received symbols. Now we can see that this is really a blind approach, meaning that we only require knowledge of P of X, so the a priori distribution of the input sequence, but not not X itself. And also the Q's can be used in conjunction with some soft FEC. Yeah, now we have really a nice loss function, but how do we actually get this decoder function? How do you actually get these Q's? CB18 suggested to use some convolutional neural network structure, which outputs then just these Q's. In this case, the CNN has to do two tasks, the equalization and the demapping. The structure is potentially capable of compensating nonlinearities, but it's an arbitrary choice. So yeah, why actually not using something we know already? So like a classical butterfly structure with fear filters, for instance. This is this linear equalizer block, and this outputs then the estimated symbols. Then we need some soft demapper in order to compute the Q's. That's no problem. In this case, the equalization and the demapping are split. This structure actually targets the compensation of linear impairments. And the state-of-the-art blind adaptive equalizer in optical communication is, as already mentioned, the CMA, which has some similar structure. In fact, this linear equalizer block is the very same. So it's also this butterfly structure with fear filters, but we additionally need some carrier phase estimation, for instance, with the Viterbi algorithm. So how do these algorithms actually perform compared to each other? For this, we did some simulation. We simulated a single polarization system with this impulse response over here, and with 2 samples per symbol. And for the VAE-based algorithms, we have some batch-wise update with an atom optimizer. The CMA is, as known, updated symbol-wise. Here we can see that for 16-QAM, actually all algorithms perform very similar. But for 64-QAM, we see a significant gain for the VAE-based equalizers. In fact, the VAE-LE, so the linear equalizer, is slightly better than the neural network one. So we further investigated this one with in a system with polarization, with probabilistic constellation shaping, and here we see even a higher gain for the VAE-based algorithm. In fact, if we now reduce the entropy, so meaning that we have some stronger shaping, we see that the CMA actually does not converge anymore, but the VAE-based algorithm stays really within 1 to 2 dB to the reference. So we now have really a system which works really well for probabilistic constellation shaping. We now also analyzed the VAE-LE with some measured data, with some experimental data. For this we used an optical back-to-back system with polarization multiplexing and heterodyne reception at 64 gigabaud. And of course, as all phase-aware algorithms, phase noise is really affecting the VAE-based algorithm. So that's why we put in CPE, so a carrier phase estimation block, after the VAE-LE in order to compensate remaining phase offset. And here we see now that even in this harsh environment for the VAE-LE, it still manages to converge. So this is really this really can be seen as some outlook, let's say. First, let's maybe conclude this talk by stating what do we have. So far we have we propose some novel blind learning paradigm for adaptive equalizers, meaning that this is really an architecture independent framework. It can really outperform state-of-the-art linear equalizers at higher order QAM formats, and there is an easy incorporation of PCS formats. Further research is needed on, as already mentioned, the convergence analysis and improvements in presence of strong phase noise, and maybe also regarding improved low complexity neural network based structures, and so on. So now I really want to thank you for your interest, and I'm happy to answer your questions.